Welcome to Math Methods Lecture 9, the lecture on quadrature. Quadrature is a historical mathematical term to determine the area of a region. In a modern context, we use this terminology for calculating integrals. Quadrature rules can be derived from the properties of orthogonal polynomials, which we discussed in an earlier lecture. Quadratures are numerically efficient ways to evaluate certain integrals, and in some cases, they even give exact results. A quadrature rule is an identity that takes an integral over an interval from a to b with a certain weight function w of x and a function f to a sum over n points of the function evaluated at some points xi with some weights wi. Here again, the capital W is the weight function of the integral. F of x is assumed to be a polynomial of degree 2n minus 1 or less, and wi and xi are the n weights and stencils of the quadrature rule. In the following, we will derive these weights and stencils for different quadratures, and I will discuss what the implications of those are. Oftentimes, we are interested in integrals where the function f of x is not a polynomial of degree 2n minus 1. In this case, the quadrature rule is not exact, but becomes an approximate expression for the integral. Despite not being exact, we can still use these quadrature rules as quantitatively improvable approximations to the integral. In particular, as we increase the number of stencils and weights that we use for the quadrature rule, the integral will converge to the exact results as we sort of improve or increase n. To be concrete, let's pick a particular example. The example that I want to talk about is that of Gauss-Hermite quadrature. Again, the quadrature rules are built by considering certain integrals. For instance, here I'm considering integrals of the form dx from minus infinity to infinity with e to the minus x squared and h of x a polynomial. The integral limits are minus infinity to plus infinity, and we can identify the weight function as just being a Gaussian, so e to the minus x squared. The particular weight function is nice because we know the orthogonal polynomials for this weight function, which is a Gaussian. In the lecture on the orthogonal polynomials, we found that these orthogonal polynomials have a name. They're called Hermite polynomials, or Hn. These Hermite polynomials are defined in terms of n or nth order differentiation of the weight function. And we can write down the first few as follows. H0 is 1, H1 is 2x, H2 is 4x squared minus 2, and so on and so forth. The polynomials are orthogonal, and in particular, they fulfill that the integral over the weight function of two Hermite polynomials with different index n and m vanish. But if n is equal to m, then they're equal to square root of pi to the n factorial. The quadrature rule we are looking for is a statement that says that we can recast this integral here as a sum over some weights and stencils where the polynomial h is evaluated at these stencils. Let's consider a trivial case first. N is 1. If n is 1, we want to obtain the stencils xi as the roots of the orthogonal polynomial hn. The n corresponds to the case we chose before. And of course, if n is 1, then we are tasked to find the roots of the polynomial h index 1, which is just x. So the only root of that polynomial is x is 0. So that means that for n is 1, the root of the Hermite polynomial gives rise to the stencil x1, which is 0. So we now have the rule saying that for n is 1, the integral here is equal to the weight w1, w1 times h of x1, and we still need to fix the weight w1. In order to do this, we sort of pick a particular integral where we take the function or the polynomial h of x to be 1. In our sort of quadrature rule for n is 1, this implies the following integral, and we can read off the value for the weight w1 on the left-hand side. It's just square root of pi. Okay, so that means that now for the n is 1 case, we have the weights and the stencils. So we find that we can express the integral over the weight function w with a function h of x is 1 as w1, which is square root of pi. And we can express the integral from minus infinity to infinity of the weight function with polynomial h of x is x, which is w1 x1, which is just 0. Okay, this is not great. We have determined two parameters, the stencil x1 and the weight w1, from two integrals, and then we can represent exactly two integrals. So we haven't really gained very much. Let's not despair for now. Let's look at the case of n is 2. For n is 2, we are tasked with finding the roots of the polynomial h2. These roots are given as plus or minus 1 over square root of 2, which defines the stencils x1 and x2. The weights are again calculated from integrals with polynomial 1 and polynomial x, giving rise to these two conditions for the weights w1 and w2, under the knowledge that we already know what x1 and x2 are. And from these two integrals, we immediately find that w1 and w2 have to be equal, and they have to be equal to square root of pi over 2. So now that we have all the roots and the stencils, we find that we can calculate integrals of this form with the weight function, but now we can calculate integrals exactly that have polynomials of order 1, x, x squared, and x cubed. All of those come out correctly. So that means that for two stencils, we have 4 integrals that we represent exactly. This is a general theme. It turns out that if we use the roots of the polynomial hn to obtain n stencils, and the corresponding weights from the integrals tx, wx of x to the n, with little n ranging from n to capital N minus 1, so these are n integrals, then we obtain exact results for integrals of this form from our quadrature rule, where little n can now go up to 2n minus 1. So what that means is that we essentially double the order of polynomials we can represent exactly with these quadrature rules. How is this possible? Well, we can explain why that works. We have used the roots of the orthogonal polynomial hn to define the stencils. If we want to represent, or if we want to look at integrals that have to do with a polynomial h of x, which is at most of degree 2n minus 1, we can represent that polynomial in the following form. So we divide out the polynomial h capital N, and we have a quotient q of x and the remainder. And we can always do this because these are polynomials, and we find that the remainder r of x and the quotient q of x are both at most polynomials of degree n minus 1. Now, since in particular the quotient q of x is a degree of polynomial n minus 1, we can write it as a linear combination of the Hermite polynomials up to degree n minus 1 with coefficients qn. So that if we take everything together and we now consider integrals with this weight function and this polynomial h of x, we write it in the two terms, the quotient or the product of the Hermite polynomial with of order n and the quotient q, and the remainder r of x. And then we use this expansion of the quotient in terms of the orthogonal polynomials. So if we do this, then if we look at this term here and we plug in the formula for the expansion of q, this becomes a sum from 0 to n minus 1 of, I apologize, there's a typo, the coefficients little qn are missing here, times hn, and the rest of the integral is the same. But the point is that since the Hermite polynomials are orthogonal with exactly this weight function, and the h little n's are Hermite polynomials of degree 0 to n minus 1, all of these integrals are 0, because we have the h capital N over here, and all of these are different polynomials, so these all integrate to 0. So as a consequence, only the integral over the remainder r of x contributes to the integral of the original polynomial here. But the original polynomial was of degree 2n minus 1, whereas the remainder is of degree n minus 1. And we sort of have built our quadrature rules that we exactly represent integrals up to degree n minus 1 out of our n stencils. So this is something we already know we've represented exactly. So basically, the reason that we get a doubling in the sort of order of the polynomials we can treat with the quadrature is because of the fact that these orthogonal polynomials here are orthogonal, and that means that essentially sort of a large number of them sort of integrate to 0. So we said that for general n, the stencils are obtained as the roots of the orthogonal polynomial of degree n. Turns out that for the Gauss-Hermite quadrature, the weights wi are actually known in closed form. They're given by this expression here. So it's 2 to the capital N minus 1 n factorial squared of pi over n squared, and the Hermite polynomial of degree n minus 1 squared evaluated at the corresponding stencil or root. Now that we have these exact form of the, or closed form of the weights, and we can also figure out the roots, let's now try to use this Gauss-Hermite quadrature as a sort of numerical approximation for a test integral. The test integral that I just made up. It's an integral that I think cannot be solved in closed form. It's an integral of a Gaussian weight and a sine of x squared minus x, which are numerically calculated by other means to be about 0.347919, and so on and so forth. So what I want to do in the following is that I want to compare this exact result for this integral with the Gauss-Hermite quadrature, where I sort of increase the order n of the Gauss-Hermite quadrature rule that I'm using, and I want to sort of see whether the result converges to the numerically calculated result here, and B, how fast it converges to that. This is a plot of exactly this process. So shown is the value of I that is calculated for this integral here. The numerical result that I showed before is shown as the solid line here at around 0.34. And then we sort of compare it with the Gauss-Hermite quadrature of different order n, where I start with n is 2, 3, 4, 5, and so on and so forth. Sorry about that. So for 2, we sort of get this value of the integral. For 3 stencils, we have that, 4, 5, and so on and so forth. And what you should see is that as we increase the number of stencils n, the order of the Gauss-Hermite quadrature, we sort of converge in an oscillating pattern towards the numerical value of this integral I. We can also check how the sort of relative error of this procedure changes as we sort of increase the number of n of the order that we use. So this is a table here where n is sort of going from 2 to 12. This is the exact result. This is the quadrature result for the corresponding value of n. And this is the relative error between the quadrature result as compared to the exact result compared from other means. So for n is 2, with the 2 stencils, we have a relatively large error, about 86%. But as you sort of increase n, this error rapidly basically sort of goes down. And by the time we sort of reach 10 stencils, we sort of have already a numerical relative error of less than 1%. And this sort of error continues to sort of go down as you sort of increase the number of stencils in this example here. So the point is that, yes, these quadrature rules can be used as a numerical approximation tool for some integrals, and they're sort of stable, and they sort of rapidly decrease the error as we sort of increase the number of stencils. Now, the example that I've given is for the case of the Gaussian weight, so Gauss-Hermite quadrature, but it turns out that quadrature rules can be defined for any integration domain, so any integral limits, or any weight function. Many of those cases have already been categorized, and I want to briefly discuss the most popular forms of those in the next few slides. The first example I want to talk about is the Gauss-Legendre quadrature. So these are quadratures of the form here, where the interval is from -1 to 1, and the weight function W is unity. In this case, for an interval of this size and the weight function of this form, the orthogonal polynomials are the Legendre polynomials, denoted as Pn of x. And then the Gauss-Legendre quadrature is set up by using the roots of those Legendre polynomials as the stencils, xi. And the weights are again given in closed form in terms of this expression here, which involves the first derivatives of these Legendre polynomials squared. Another case is the Chebyshev-Gauss quadrature. Again, same interval from -1 to 1. Here the weight function is taken to be 1 over square root of 1 minus x squared. The corresponding polynomials here are the Chebyshev polynomials Tn of x. And as before, the quadrature is set up by taking the roots of the Chebyshev polynomials of order n and the weights, except that in this case, the roots of the Chebyshev polynomials are known in closed form. They're given as the cosine of 2i minus 1 pi over 2n, and the weights are given as pi over n. So this is one of the cases where everything about the quadrature rule is known in closed analytic form, both the roots or stencils and the weights. So we can sort of write down very high order versions of these Gaussian quadrature rules for the case of this particular weight function. The last example I want to talk about is the Gauss-Laguerre quadrature. So this is an interval from 0 to infinity with a weight e to the minus x. And here the orthogonal polynomials are the Laguerre polynomials, denoted as ln of x, with the quadrature again set up as with the stencils as the roots of the Laguerre polynomials, and the weights again given in closed form. Now again, sort of there are a number of other cases that are known, and these, for instance, there's sort of a Gauss-Jacobi quadrature that uses the Jacobi polynomials, but the sort of rule is always the same. We sort of look for the orthogonal polynomials for a given weight function, and then we sort of define the stencils through the roots of these polynomials, and we have to figure out the weights. Now, it turns out that we can use this procedure also for the cases that have not been previously cataloged. So you can build your own quadrature. Let's say that, for an example, let's take a case where there is a weight function, which I take to be e to the minus x to the 4, where the polynomials for this, orthogonal polynomials for this case, are not named. However, there still is a quadrature rule of this form, and we can sort of construct the orthogonal polynomials by the same sort of procedure that was outlined in the lecture on the orthogonal polynomials. And once we have the polynomials, we can find out the quadrature stencils from the roots and the weights from these integrals with the weight function x to the n, where the little n ranges from 0 to n minus 1. And this will sort of generate quadrature rules for integrals of this form. This brings me to my summary. We discussed quadrature rules for evaluating particular integrals. We learned that the quadrature rules are built from the roots of the orthogonal polynomials that correspond to the integral weight function. The quadrature rules built with n roots and weights provide exact results for integrals of polynomials of degree 2n minus 1. So we basically double the sort of number of exact results that we have. Quadrature rules exist for a large number of cases where we have intervals and weight functions. And these quadrature rules can also be used to obtain numerical approximations for integrals that sort of are hard to calculate in other form. Thank you so much for your attention.